going on 23 years, or over 23 years now. All right, so again, I'm Chris Boone, so I'm the project scientist for the atmospheric chemistry experiment, and I work at the Science Operations Center at the University of Waterloo. So I'll start off with, Start off with a very brief overview of the mission. Right, so we're a Canadian-led satellite mission for remote sensing of the Earth's atmosphere. We've been in orbit for a long time. Right, so we currently have over 19 years worth of scientific data. So the primary instrument on board is a high-resolution Fourier transform spectrometer, ASFTS, with a broad spectral coverage in the infrared. We also have a UV visible and near-infrared spectrometer called Maestro on board, and two full sun imagers that with wavelengths chosen to match those from SAGE, so 1 micron, half micron. All right, so probably don't need to go into too much detail on this for this crowd, but our measurement technique is solar occultation. Right, so we're staring at the sun through the limb, and as the satellite progresses in its orbit, we collect a series of measurements as the sun rises or sets from the satellite's point of view. So we generate a set of spectra that range from high altitude, where you only have a few molecules significantly contributing to the spectrum, down to about 5 kilometers, where you have dozens of molecules contributing. All right, and this set of measurements allows you to fairly directly infer altitude variations for the constituents. One of the drawbacks of this approach is our geographic coverage. We only have 30 sunrise, sunset events per day. But because we're using the sun as a light source, they're very high quality measurements. And we're self-calibrating because we can look at the sun before it goes through the atmosphere. All right, so again, excuse me, the infrared spectrum is a very rich, a very rich region in terms of spectroscopic information. Pardon me. Right, so we have dozens of atmospheric constituents that we retrieve with the addition of 2 additional molecules from version 5, ASFTS version 5 processing, HFC32 and HOCl. We're now up to 46 different data products. And on top of that, for a number of the molecules, we can actually measure subsidiary isotope logs. So for water, ozone, CO2, N2O, we can get isotope substituted species. We also provide pressure and temperature as a function of altitude. And from the imagers, we get aerosol extinction profiles. But on top of that, the infrared spectrum from the ASFTS gives us a unique, valuable source of composition information for the aerosols, which I'll talk a lot more about in the coming talk. And we're not done, despite all the over 70 data products currently available. There are more in the works. So there's one for which the microwindow set is already finished, and there's some additional weak absorbers that I'm looking at adding to the data product for the next version, or a future version. And on top of that, there's another new data product for ASFTS version 5, and that's line of sight winds. So we have a very sensitive instrument, so we're able to detect the tiny amount of stretching in the wave number scale that occurs from the molecules moving relative to the satellite from the winds. And again, line of sight only, but there is some hope of adding vector winds, so north, south, east, west component winds. So the dots in the plot here show the locations of the measurements on a particular day. Green sunrise, red sunsets, and they're all at very close to the same latitude. And if you look at the wind speeds for that day, wind speed profiles for that day, the sunrise and sunset profiles are near mirror images of each other. So they're looking at different directions through a fairly stable wind field. And for the sunrise measurements, we look forward and off to one side relative to the orbital motion. The sunset measurements, we're looking backwards and off to one side. So the two directions aren't exactly opposite, but you have two different measurements, or 2 different angles through the wind field, which should allow us to clutch together vector winds for this day. But even if we only have line of sight, they're still valuable, for example, for validation studies of other vector wind data. So the plot up here shows a comparison of our wind data to some meteor radar data, sets of ground-based measurements that look at the movement of meteor ablation trails driven by the wind. And for the relatively small altitude range for the meteor radar data, you can see there's a very good agreement between them and our data. And one extra benefit that we have is we have a very large altitude range, so we can go from 20 kilometers up to 135 kilometers, which fills in a fairly dead region in the coverage of winds measurements for the atmosphere. All right, so as I said, we're getting long in the tooth. We've been up there for a long time, 19 years, over 19 years worth of data, with a very stable instrument, self-calibrating, which is great for looking at trends, so variations in time of VMRs or concentrations. And because we measure so many different molecules, you can intercompare the trends for different molecules and put together a bit of a story. Right, so for a number of molecules that we measure, CFCs, HCFCs, HFCs, HCFCs, there's a bit of a turning point in the trends around 2012, which is presumably related to the Montreal Protocol. All right, so for chlorine-containing molecules, there's either a faster decline for CFC12 or a slower increase for the HCFCs after 2012. And around the same time, if you look at the CFC replacement HFCs, like HFC 134A, HFC 23, there's a faster increase in their VMRs. And then a couple years later, around 2014, there's a faster increase in stratospheric CF4. Right, so the trends for all the other molecules on this slide are for the troposphere, and so it takes there's going to be a couple-year lag for the extra fluorine being pumped into the atmosphere to make its way up to the stratosphere. And there's a couple of other molecules which have a turning point around 2012 that don't quite fit into the same story. One of them is CFC11. So unlike CFC12, the decline actually flattens off, so you had a slower rate of decline rather than a faster rate. And this has been attributed to some illegal production for this compound, which I believe has since been halted, so CFC11 should start coming back down again. And our stratospheric HCl had a flattening of its decline starting around 2012. But as I mentioned, changes in the troposphere should take a couple of years before they start to manifest in the stratosphere. So something else is going on with HCl, and it's presumably associated with no longer having significant contributions to the decline, to the decline from shorter-lived chlorine-containing molecules such as methylchloroform. Right, so they've dropped to such low levels that they're no longer contributing to the decline. And we're more into a long game, a long waiting game for the longer-lived molecules to start to drop off. All right, so if you're interested in a particular molecule, with dozens of molecules and 19 years worth of data, there's a good chance you'll find something interesting about that molecule in our data set. And because of time, I can't go through all of them, so I chose a particular interesting example for N2O, or high-altitude N2O. All right, so between the time we launched in August 2003 and the time we started our scientific measurements in February 2004, there was actually a very large solar event. I think it's called the Halloween event from 2003. So our very early measurements were actually probing the aftermath of that event, right? So auroral activity from the solar event. And so looking at NOx, so NO plus NO2, you can see this tongue of enhanced NOx descending in the atmosphere. And this was completely expected. So NOx production had been seen many times from auroral activity before this. But what was surprising is that we also saw enhanced N2O descending through the atmosphere. So and a later study shows that this was not an isolated event, that there is a periodic production of N2O in the lower thermosphere that then descends down into the stratosphere, which has so it's a source of stratospheric N2O, which has implications for ozone in the stratosphere. And because we measure many molecules, multiple molecules, we can look at synergy between the different molecules. Right, so on the left here, we have an example of a study looking at chlorine partitioning in the polar vortex during winter and spring. So the red points here are the data points within the polar vortex. And so we have HCl, chlorine nitrate. So early in the winter, HCl and chlorine nitrate are reacting on the surface of polar stratospheric particles, so both exhibit a decline as they react and form other molecules. And HCl goes close to zero during the middle of this time period, whereas chlorine nitrate actually starts to go up. So ClO is one of the products of the reaction between HCl and chlorine nitrate. And ClO will combine with NO2 to give you chlorine nitrate. So the balance of the chlorine partitioning goes heavily towards chlorine nitrate during the winter months. But then as you get into spring and the polar vortex starts to break down, the partitioning between the two molecules goes back towards normal levels. And because we measure so many chlorine-containing molecules, you can actually put together a budget for chlorine in the atmosphere and see how it changes over time. And kind of an extreme example of looking at synergy in the data set, so looking at a bunch of different molecules, you can infer chemistry on aerosols from the behavior of the molecules. Right, so when you have extremely strong fires on the surface, you can get smoke directed or injected directly into the stratosphere. And it turns out there is chemistry that can occur on the smoke particles. Right, so during late 2019, early 2020, there was a series of extremely strong brush fires in Australia. So at the time, it was dubbed Australian Black Summer, but since then it's been renamed Australian New Year fires. But at the altitudes, so just below 20 kilometers, the altitudes where you see these smoke particles, we observed some declines in ozone levels. So these plots here show the average ozone levels for a particular time period for the latitude range 45 to 60 degrees south, so the vicinity of Australia. And if you look over time, so 5 months after the fires up to about a year after the fires, you can see there's a distinct, so the red curves are from 2020, and the black curves are the average values from all other years, right? So you can see in almost a year after the fire, there's a distinct lower value of ozone near 20 kilometers. And you can go through, again, synergy, looking at all the different molecules in ACE. So looking here at the chlorine-containing molecules, HCl, chlorine nitrate, HOCl, ClO, there's actually massive chlorine processing on the smoke particles. So you have HCl reacting somehow and generating chlorine nitrate. So whether it's going to ClO and then chlorine nitrate, we don't know yet. But however it works, you're getting a lot less. Again, red is 2020, and black is all other years. You're getting a lot less HCl in 2020 and a huge amount more chlorine nitrate. And you're also generating HOCl and to some extent chlorine ClO, chlorine monoxide. But because we're measuring solar occultation, we measure in the sunlight, you can't have a large amount of the chlorine ClO accumulating. So it's going to go to something else. But you can still see there's a bit of a extra bump in 2020. And on top of the chlorine processing, there's also perturbations in other chemistries. So the nitrogen chemistry, NOx, and the OH chemistry, looking at various molecules. So there's a lot going on here that in the end is contributing to chemical destruction of ozone at mid-latitudes from these fires. And more recently, we've seen some perturbations in the ozone concentrations associated with the Tonga eruption that's been mentioned previously and will probably be mentioned many more times during this week. Right, so extremely strong volcanic eruption. So it occurred January last year, but you still see significant significant enhancements in stratospheric sulfate aerosols to date, so over 16 months later, and particularly in the Antarctic, which could have implications for ozone with the onset of southern hemisphere winter coming. But for the example here, I'll show here is for near the tropics, or in the tropics, so 0 to 15 degrees south. So these are the average profiles from August, about 7 months after the volcanic eruption. And similar to the previous slide, you have 2022 is a separate color, and then all the other years are in blue this time instead of black. So here we have nitric acid on the left, NOx, so NO plus NO2 on the right. And it looks like there's some stratification happening. So there's an altitude dependence to the chemical reactions, the chemical effects that are going on. So at high altitudes, you're getting an enhancement in NOx. And at lower altitudes, just above 20 kilometers, so near the sulfate aerosol layer peak from Tonga, you're getting low values of NOx. And about the same altitude, you're getting a huge enhancement in nitric acid. Right, so what's going on here is that N2O5 is reacting on the surface of the sulfate aerosols and being converted into nitric acid. And N2O5 serves as a nighttime reservoir for NOx. So when N2O5 goes away, you have lower levels of NOx. And NOx is strongly involved in ozone chemistry. Right, so wherever you have high values of NOx, you're going to have more ozone destruction, less ozone. So looking at our measurements for ozone for the same region, same time period, you see at high altitudes you have low levels of ozone, and where you have low values of NOx, you have less ozone destruction, so you have ozone levels are relatively higher. But it's not quite that simple. So if you look at the entire data set, right, so it goes from the equator down to the poles, a lot is happening, right? So things are changing as a function of latitude, altitude, time. There's perturbations in the nitrogen chemistry, the chlorine chemistry, and the HOX chemistry. And there's also seems to be some dynamics going on, which we can hopefully track by doing correlations with that are induced by this extremely large volcanic eruption. All right, in the last few years, we put a lot of effort into induced by this extremely large volcanic eruption. All right, in the last few years, we put a lot of effort into extracting aerosol information from the ACE-FTS. Right? For those of you who remember your first year chemistry labs in university, the infrared spectrum contains a lot of information on composition. Right? So just looking at the shape of a spectrum can often let you identify the aerosol type just at a glance. All right, but the problem with looking at aerosol spectrum from the ACE-FTS is that there's a lot of clutter in the way, right? So there's all the gas phase lines on top of it. So you have to get rid of those. But fortunately, we do retrievals for all the gas phase lines, and we just remove their contributions, divide out a calculated spectrum containing all the known contributions to the spectrum. And whatever's left over, I call the residual spectrum, which contains aerosol spectrum plus some leftover junk. And I like to get rid of the leftover junk by calibrating using a measurement that is at background aerosol levels. That's the blue curve here. So the red curve is a sulfate aerosol spectrum from the Rayokoki eruption. And just looking at it, you can tell it's sulfate, right? So you have a series of peaks from sulfuric acid. You have a peak 1700, broad peak, OH stretch peak, near 3000 from the water and the sulfuric acid in these droplets. So looking at the background spectrum, The most prominent features here are from nitric acid. So there's a number of missing bands of nitric acid in the line list. So they cannot be included in the calculation, so they do not get removed when you generate the residual spectrum. But if you just divide out your target spectrum by the calibration spectrum, then these junk features go away. And what you're left here is with is this quite pretty sulfate aerosol spectrum in the lower panel. And you can use this to determine or to do quantitative fit, right? So you can determine size, composition. So for sulfate aerosols, the amount of H2SO4 is in the droplet. And for sulfate aerosols, you know the shape, right? It's a spherical droplet. But for other aerosols like ice, you can find shape parameters as well. And it may be hard to see. So the red, beneath the red curve is a bunch of blue points that represent the fitting results. So using laboratory measured optical constants for aqueous H2SO4, you can fit the spectrum to get your size and composition information, and it fits extremely well. And the ability to reproduce the spectrum, the aerosol spectrum, using laboratory data, serves as an implicit verification of the type of aerosol. If it's a different type of aerosol, you would not be able to reproduce it by using sulfate aerosols, optical constants. Right, so one of the most interesting studies we did with our aerosol spectra was looking at smoke particles. Right, so again, you have very intense fires injecting smoke particles into the stratosphere, and we've measured a number of such events over the course of our mission. This top plot shows the calibrated residual spectra for 3 such events. Right, so in blue is a measurement from Australian Black Saturday in 2009, so another strong brush fire. In orange is 27 Pacific Northwest event, and in red is from Australian Black Summer. And what was surprising, the most surprising finding, was that the shape of all these spectra were quite similar. So there's some variation in the relative intensities of some of the spectral features, but they all looked extremely similar, right? So they're consistent with oxygenated organic matter, probably some form of carboxylic acid. And I've indicated some of the more prominent features, right? So the carbonyl stretch, a sharp feature here. In this shoulder is a CH stretch and an OH stretch. And if you're really keen, you could go through and identify all the features here in the fingerprint region. So the methyl deformation, the CH bending, and the OH bending, and the CC stretch. But the pertinent thing is that at a glance, you could just identify that you have smoke in your spectra. So unfortunately, we don't have optical constants for smoke that we could do a quantitative analysis and find the size and whatnot. But we do have a consistent shape that we can use to determine when we're measuring smoke. And on top of the aerosol information from the ACE-FTS, we also have biomass burning products, right? So we can see peaks in the VMR profiles for a number of products or number of molecules that get released when you have large fires like CO, HCN, C2H6. And that serves as a confirmation that you're looking at a fire, I guess. Right, and on top of that, we routinely measure ice features. We see a lot of ice features in ACFCS spectra. And the interesting thing about ice is that the size of the particles, the size of the ice particles will determine what the spectrum looks like. You see a very diverse set or diverse shape of the spectrum depending on how big they are. Right, so in the upper left, we have ice particles from polar mesospheric clouds. So these are clouds at very high altitude when you have extremely cold temperatures near the mesopause during summer solstice or near summer solstice. And these are relatively small, so the order of few microns. And the spectrum is a pure absorption, right? So you have a nice OH stretch feature here and a libration feature. And if you move further down the atmosphere, look in the stratosphere, pull the stratospheric clouds, so type 2 clouds, The size of the particle is somewhat larger, about 50 microns or so. And you see a combination of absorption and scattering in the extinction signal. And move a little further down, you have cirrus clouds in the upper troposphere. And these are even larger. They're bigger than 100 microns. And the signal is dominated by scattering. So you don't see much, you see a little bit, but not much from absorption. It's mostly scattering. But if you look at the red curves here, which are the fitting results for these spectra, we can reproduce fairly well the ice spectrum, regardless of the size and shape of it. Right. So using optical constants measured in a laboratory, we can determine the size and shape parameters for the ice particles. All right, so looking at some other aerosols, so PSCs. So the prevailing wisdom is that there are 3 types of PSCs. So the type 2 ice PSCs and 2 type 1 PSCs, nitric acid trihydrate, NAT, and supercooled ternary solution, SCS, which is a liquid droplet of water, sulfuric acid, and nitric acid. But we discovered there's actually a 4th type of PSC, and that's we called supercooled nitric acid, which has extremely low levels of H2SO4, diagnosed by the lack of a strong sulfate feature near 1200 weight numbers. Right, so it's mostly just water and nitric acid, so a liquid droplet. And the usual assumption for the formation of SCS is that you have nitric acid condensing onto an existing sulfate aerosol particle. So this discovery suggests that we might have to rethink how some PSCs are formed, and it's going to change the chemistry as well. So the composition of the substrate is going to affect these reactions that occur on the surface of polar stratospheric clouds that impact ozone concentrations in the polar vortex. And continuing on, we also measure ash. So with our geographic coverage, we're often a couple of weeks late when measuring the plume, or a couple of weeks after the eruption when measuring volcanic plume. And by that time, volcanic ash often has already settled out. So these are larger particles, they sediment quickly. But there are some instances in our measurement set where we see ash, and one in particular, the Cordon Calais, was almost all ash. So there's very little sulfate aerosol. It's all silicate. And over here, there's the Khaloud eruption in 2014. There's actually fairly even amounts of ash and sulfate aerosol. So the orange curve here is a fit for the sulfate contribution to the aerosol. And in the residuals, you can see this very large silicate spectral feature. And when you're dealing with aerosols, you don't always see a nice single type of aerosol, nice ice only or NAT only or whatever. You often see a mix of various aerosol types. So we're actually working on simultaneously analyzing multiple aerosol components, right? So it'd be nice to know how much the aerosol is ice, right? So you have this, in this example, you have a combination of ice and either an SCS or supercooled nitric acid. You can see the ice feature fits well, and the supercooled nitric acid feature fits fairly well. So this is just first stages, but it looks like we can extract information on multiple contributions to the composition of aerosol particles. Excuse me. All right, there has been a long-standing uncertainty of the contribution of sulfate aerosols to climate, right? So for years, it has been well known, well documented that we don't know what sulfate aerosols are doing for climate. So you don't know if they're cooling, don't know if they're heating, or some combination at different times or whatever. So we decided to use our composition information from the ACE-FTS to try to dig down on this subject, to see what we could say about sulfate aerosols in climate. Right, so scientific studies typically assume a composition of sulfate aerosols of 75% H2SO4 by weight. So this is, just a convenient value. I don't think people actually believe that that's an accurate value. It's just convenient. But based on our results, we'd say it's more close to the maximum value that you would see in the atmosphere rather than a typical value you'd see. All right, so from ACE-FTS spectra, I generated composition information from over 5,000 measurements following the Rheacoke volcanic eruption and 2,000 measurements following the Tonga volcanic eruption. And the results are plotted here. Right? So there's a false color scale for composition, weight percent H2SO4, temperature on the y-axis, and the log of the water vapor pressure on the x-axis. And if you look where you have high temperatures, low water vapor, like in the stratosphere, then yes, definitely the composition is close to 75% H2SO4. But as you go down in temperature and up in water vapor content, right, so you have to have a thermodynamic balance of the vapor pressure from the droplet and the vapor pressure in the atmosphere. So the droplet is going to take on more water, and at low temperatures and high water vapor pressure, you can get down to like 50%, the order of 50% sulfuric acid. But we do provide, so these data fit well, so you can reproduce these data to within about 5% using a empirical function. So if you have some other knowledge of temperature and water vapor, then you can actually calculate an accurate value of the composition rather than using just the standard 75%. All right, so we decided to push the analysis of our data further, right? So we have our ACE-FTS residual spectra, but in the infrared, the spectrum is not very sensitive to the parameter size, the particle size, right? So it's mostly absorption in the infrared with a tiny bit of scattering. So we decided to combine our data with the data from Stage 3 on the International Space Station, Stage 3 ISS data, right? So you have near-infrared visible data points, and in that wavelength region, the spectrum is extremely sensitive to size parameters, right? So by combining the infrared and UV visible, or UV infrared, near-infrared, you get a much broader wave number range, right? So in these analyses, we assume the typical log normal distribution. And to do the analysis, we normally just fix the size distribution and fit for size, median radius, the size parameter. But by having such a large wave number range, large wavelength range, you can actually fit for both. You can determine median radius and geometric width for the log normal distribution. And for this, we chose extreme close coincidences. So you want to make sure that you're measuring the same air mass. So the coincidences were within a few minutes, a fraction of a degree in latitude, and about 1 degree in longitude. And we used 1 micron information, so the 1 micron channel from the SAGE data compared to the 1 micron aerosol extinction profile from the ACE satellite, just to make sure that they agreed reasonably well and we were looking at the same air mass. All right, so the procedure we use is fairly simple. So take the ACE transmittance data, calculate transmittance data points from the SAGE data, so from the reported extinction profiles using the ACE-FTS measurement geometry and field of view. We discarded 1 data point from SAGE. I won't go into that from time. And we use different optical constants for the 2 regions because we don't have one that covers the entire region. But all right, so the interesting thing we found was that you could not properly reproduce the data, the combined transmittance. So these 8 data points on the right are from SAGE, and all these data points here are from ACE. And in the analysis, I overweighted the SAGE data points to make sure that they drove the results rather than the 1,200 plus data points from ACE. And you can see from the monomodal fit on the left, so there's some systematic features in the SAGE data and the ACE data. The extinction is dramatically underestimated. Whereas if you use a bimodal distribution, right, so you use 2 sets of median radius and geometric width, then things fit much better. And on the right here are the different contributions to the extinction from the 2 modes. So the fine mode is the mode with the lower median radius. Coarse mode is the mode with the larger median radius. And the reason this works is that there are resonance effects in me-scattering, right? So with the absorption in the infrared in the ACE-FTS region, it's just Beer's law. So you have the light traveling through the aerosol being absorbed. With me-scattering, there's resonances that will peak somewhere in the vicinity of the diameter of these droplets, these spheres. So the coarse mode, which have a diameter of the order of 400, 600 nanometers, actually peaks somewhere in the SAGE wavelength range, whereas the fine mode has a peak that's off the screen, right? So it's somewhere in the ultraviolet. And by tuning the relative contribution of these 2 different modes, you can reconcile the absorption in the ACE-FTS spectra with the scattering effects in the SAGE region. And I'll go through it quickly, but you see similar effects in Tonga, but the coarse mode actually dominates in this region. So even in absorption, so you have much larger sulfate aerosols from Tonga than you had from Ryukoke. And it's a bit more subtle, but you can, if you look at an example of a background sulfate aerosols, you see an improvement in the residuals using a bimodal mode compared to using a monomodal distribution, bimodal distribution versus monomodal distribution. So if particularly look at the peaks in the sulfate aerosol spectrum in the infrared, right? So this peak near 1200 and the OH stretch peak near 3000, you see much smaller residuals. So particularly in the background case, the number density for the fine mode is significantly larger than that for the coarse mode, but because of resonance effects, you can actually get a stronger contribution to this extinction signal from the coarse mode than the fine mode, such as here at 1 micron. Okay. All right, so the implications of this are fairly profound, I would say. Right, so the role of sulfates in climate is not well understood. I think part of that is because most scientific studies assume a monomodal distribution, fine mode only, even though the coarse mode at some wavelengths has a stronger contribution to the signal and cannot be ignored. And of course, this is mostly due to the information content in the measurements, right? So you don't have enough information content to separate out the contributions from the different modes. So the obvious fallback is to say just assume monomodal, but there will be a penalty for that, which I've shown. All right, and most of the information that we get for aerosols comes from visible near infrared, so SAGE, OMPS, OSIRIS. And if you analyze such data using a monomodal distribution, you'll likely get an underestimation of the absorption in the infrared region, right? So the greenhouse effect, the absorption in the infrared contributes to the greenhouse effect from the sulfate aerosols, which is a big deal. All right, summary, I made it. All right, as I said, SciSat coming up on 20th anniversary in orbit, so it's approaching 2 solar cycles, which is great for looking at trends. So I can separate out the solar effects, getting into the microphone. So it's continuing to operate well, so it provides information on dozens of molecules, good for science and validation studies. And I would say the recent focus on aerosol information from the ACE-FTS has provided quite valuable insight into sulfate aerosols in particular. So this is a source of information on composition that you really can't get from anywhere else. So the aerosol spectrum in the infrared region from ACE-FTS. So we provided an empirical expression from which you can calculate aerosol composition, assuming you know temperature and water vapor pressure, and showed that if you assume a monomolar distribution for sulfates, at least in a certain range of conditions, it's not particularly accurate, which has major implications for climate. And in the future, so this other instrument on board, Maestro, operating in the visible near infrared, is cleaning up its aerosol extinction data product. So in the future, if we can combine the infrared information from ACE-FTS and visible near infrared from Maestro, I'd say we have a powerhouse data setup, because every measurement, so unlike SAGE, where you only have a very small number of coincident measurements, extreme close coincidence, every single measurement is going to be coincident for ACE-FTS and Maestro. And thank you for your attention.